Finally, we're going to look at a summary review of applying quadratic models. So first thing, can you sketch a graph of a quadratic by hand, starting with the base graph y equals x squared, and then apply the appropriate transformations in the correct order? For example 1, we're going to use transformations to sketch y equals negative 1/2 x minus 4 squared minus 5. So we're always going to start with our base graph, y equals x squared. Next, we need to apply the transformations in appropriate order, starting with the magnitude of the a value, which is 1/2. So we have y equals 1/2 x squared. So we're going to compress the original graph by a factor of 1/2. So take all the y values and divide them by 2. Now we deal with the negative. So we have y equals negative 1/2 x squared, which means we have a reflection across the x-axis. So take all the y values from the red graph and change them into negative y values. So finally, we're going to take and apply any translations. So in this case, we have a h value of 4 and a k value of negative 5. So this means we're going to move 4 units to the right and 5 units down. So take every point on the green graph and move them 4 right and 5 down. Next, can you describe the transformations of a quadratic you would apply to the graph of y equals x squared in the order you would apply them to obtain the graph of a quadratic relation? So for example 2, what transformations would you apply to the graph of y equals x squared to create the graph y equals negative 1/2 x minus 4 squared minus 5? So same as the equation given in example 1. Now instead of graphing, we're going to describe the transformations. So starting with the magnitude of the a value, we're going to have a vertical compression by a factor of 1/2. Next, we deal with the negative if it has one. So this is a reflection across the x-axis. And finally, let's look at the h and k values. And they tell us we're going to translate 4 units right and 5 units down. And there are the transformations in the order you would apply them. Next, can you determine the equation of a quadratic in vertex form, given the vertex and any other point on the parabola? And then could you express that quadratic relation in vertex form as an equation in standard form? So example 3, determine the equation of the parabola in vertex form, then rewrite the equation in standard form. So remember, vertex form looks like y equals a x minus h squared plus k, where h and k are the coordinates of the vertex. So if we look on our graph, here's our h and k value, and we see that we have 4 and 2. So if we sub that into our equation, we get y equals a x minus 4 squared plus 2. Next is a sub in any other point. So let's find a point on this parabola. So we could take a point here, a point here. So let's say we take the left one. That's 1 and 5. We're going to sub that in for x and y in order to get our a value. So we have 5 equals a 1 minus 4 squared plus 2. So 5 equals a. 1 minus 4 squared is negative 3, and negative 3 squared is 9. So we have 9 a's plus 2. Move the 2 over, and we get 3 equals 9a, or subtract 2 from both sides. And then divide both sides by 9, and we end up with a equals a third. So therefore, a quadratic in vertex form is y equals 1/3 x minus 4 squared plus 2. Again, this is our vertex form. Next, we need to get this equation in standard form. So to do that, we are going to expand this expression. So we get y equals 1/3 x minus 4 plus 2. We're going to distribute a pair of brackets, and that gives us 1/3 x squared minus 4x plus 16 plus 2. If we collect like terms, we get 1/3 x squared minus 8x plus 16 plus 2. We can now distribute the 1/3 into the bracket. We get 1/3 x squared minus 8 over 3x. Recall that's 8 over 1, that's 16 over 1. And then plus 16 over 3 plus 2, and remember that is 2 over 1. So the last thing we're going to do is collect our like terms that we have here. And we get y equals 1/3 x squared minus 8 over 3x. 2 over 1, that's the same thing as 6 over 3. And that's going to leave us with positive 22 over 3. So there is our equation in standard form. All right, next topic. Can you express a quadratic relation in standard form as a quadratic relation in vertex form using symmetry or partial factoring, which mean the same thing? So recall, for partial factoring, we have a quadratic. In this case, it opens down. And what we're going to do is we are going to find the y-intercept and its corresponding point, which is equal distance from the axis of symmetry, in order to help us find the vertex. In standard form, we know the y-intercept is the c value. So we have the y-intercept, and we're going to let y equal the c value. So we start off by saying let y equal -3. And this gives us -3 is equal to -2x squared plus 16x minus 3. The only way to solve quadratics is to get 0 on one side. So if I add 3 to both sides, I get 0 equals -2x squared plus 16x. Next, you're going to factor, but remember to common factor first. So we take out a -2x, and that gives me x minus 8. And notice we've already factored that expression. We're now going to find the zeros for this quadratic, or what we call the roots of the expression. And the roots for this one are x1 equals 0, because -2 times 0 is 0, and x2 is equal to 8, because 8 minus 8 is 0. Once we have the roots of this expression, we can now find the axis of symmetry, which is x equals 0 plus 8 divided by 2, which gives us an axis of symmetry of 4. Optimal value we can find by subbing in the axis of symmetry into the equation given above, so -2x squared plus 16x minus 3. So -2 times 4 squared plus 16 times 4 minus 3. Let's check that again. Good. And that gives us 4 squared is 16 times -2. That's -32 plus 64 minus 3. And if we add all those terms up, we end up with 29. So therefore, our vertex is 4 and 29. If we're asked to graph this quadratic now, we have 3 points. we have our vertex, which is at 4 and 29. So 4 and 29. We have two other points we found here. We know the x values, and up here we said that y equal -3. So what we have are the points 0 and -3, our y-intercept, and its corresponding point 8 and -3. So if we add those to the graph, so 0 and -3 would be somewhere here, and 8 and -3 would be equal distance from the axis of symmetry and the same height as the y-intercept. So this is good because our parabola opens down, and from our equation we saw that there was a negative a value.